All right, thanks everyone for coming to my talk. This is a talk about a library that I was developing last year, and I found some interesting things to talk about. The next slide. Oh yes. So the alternative title here is The Unreasonable Effectiveness of Boolean Algebra. Because Boolean algebra is something we'll learn in college or high school, and we're sort of aware that it's underpinning everything we do, but we don't kind of see that in our day-to-day, right? And so I thought I'd put it in this talk. My usual disclaimer applies. There's no ChatGPT or any other kind of LLM material here. All the mistakes are mine. Please do ask any questions as we go. So this talk is about a message handling library. Many of us probably have done message handling. Who in the room has some kind of message handling in their code base? Yeah, right, probably 3/4 of the room. So we're going to talk a little bit about this particular library, which will be, I'm sure, similar to some that other people have. But in particular, we're going to talk about how code matches in this library, and how Boolean algebra kind of unlocks some things there, and a few other things along the way. So I would like to thank Augustus de Morgan and George Boole. Again, their work underpins everything we do, but we don't really think about it day to day. So to begin with, I just want to introduce you to some of the nouns of the library, i.e. the fields and the messages. So in this library, a field is a type, and that type contains a name and the C++ type of the field, like uint32 or something like that. One or more field locators, so where that field is going to be in the message layout. Right? We're talking about a message as a bunch of bits wire, and then that's raw storage, raw data at that point, and then the idea of messages that we sort of overlay a view on that storage, and we can then match against what various field values are. Right? So that's the idea here. So in the embedded world that we currently inhabit, field locations are conventionally specified with 3 items: the D-word offset of the field, and then the most significant bit and the least significant bit. And it's an inclusive range. With a closed range, so we're including both ends of that bit range. So what does that look like in something that might be familiar? Here's the IPv4 header, straight off of Wikipedia. And there are some fields in there. And, so if we look at the first 4 fields, the IP version, the internet header length, and the DSCP and ECN, what they stand for doesn't matter. In C++, in this library, those declarations look like this. So the declarations of those fields are types. So we can see that version is a field, right? A name version. Its type, sort of on the outside, is going to be uint18. And it has a location, which is at the 0th D word, bits 0 through 3 inclusive, right? And so on for IHL and DSCP and ECN. Everyone happy with this? Yep. Okay, so these are just types, remember, at the moment. Now these fields need some behavior, and the obvious kind of behavior that they need is a way to read and write themselves into that message storage. So that's what extract and insert do. So we take a range, that's the underlying data, and the field knows how to extract those bits and present them back as its own type. So that's the uint18, right? Or on the other way around, how to insert the value of the uint18 type into those bits in the range. And in my world, the range is usually like a stood array of uint32Ts, but it can be, it's anything that satisfies a range. It could be a range of uint8Ts. It could be a span. It's just a range. Okay, so that's the field design. So a field is an empty type. It's 2 separate things: the spec, which is the name of the type, and the location, or the locator, right? And these are separated because the same field name and type might occur in different messages in different places. So it makes sense to separate those two things. Location. So like I said, the usual convention is D-word offset, most significant bit, least significant bit. But there's a perfectly fine alternative convention, which is just roll that D-word offset into the bit range, right? These are saying the same thing. They're just different conventions for specifying where that flags field is. Right? So 50 is 32 plus 18, which is the most significant bit. We can also have another use case here. And it's not a common one, but it is a use case I was asked to provide. A field might be split across multiple disjoint locations in a message. I see some people nodding, people who have embedded experience are nodding for this. So, you know, this is saying split is a field, which is a UNAT, but in the layout, its parts are located in two different places, right? And so that's what that looks like as a declaration. Okay, so you've noticed here I'm using user-defined literals, right? And that's because I wanted type-safe design in this library. And so those user-defined literals boil down to plain enum structs, right? Strongly typed integral types. That's what enum structs are. And the user-defined literals just give you a thing of that type. Now, before I came to this library, they were just plain ints or maybe unsigned. But in that case, you know, you can see how you can swap over parameters, and it might be bad if you do that. But now, because of type safe design, we have safety there. And this at locator, again, for the two use cases, the two conventions, we just provide two different specializations, and these are just aggregate types, right? These are just types which have in them literally the three things or the two things, right? Depending on what you make them. That's all they are. And given that, these conform to a common interface for location, and this is the interface, right? So whether or not we have that D-word index, you can probably intuit how we can implement these four functions, right? You can compute the index from most significant bit, least significant bit, if you don't have it. And the size here is the size in bits. Everyone happy? Everyone good? No questions so far? Great. So given all that, we can write a couple of concepts that tell us about locators, right? We can write a concept to say, is this an extractor? Well, a thing is an extractor for a field. When we give it a span, we can call extract, right? And it can give us back something of that field type. The inverse applies for an inserter, right? We're not going to call extract, we're going to call insert with a value and the span. And the locator is something as an inserter and an extractor, so it's a locator. So everything we talked about so far is the nouns of the library and kind of the concepts. It's fun.
So do you support static extend span?
Does it support static extend?
Yeah, you only have the interfacing concept with dynamic extend. Are you happy with that, or?
I see. Yes, it supports. Yeah, this is so right. Okay, so the span here is a fixed type just for the purpose of writing the concept. Like you can't. I couldn't say any kind of span because concepts don't work like that, right?
Yeah, I know.
Yeah, I know you know, but so yeah, so the way the concepts are written here, I fix the type of the span. Just like if you can do it for this span, you can probably do it for anything. Is the idea. But yes, concepts don't allow you to be generic in the type of span there. Sort of a different thing. Okay, thanks for the question. Yes, that's one. Yeah, it's not the case that the span has to be that kind of span. That's just representative. Okay, so fields and empty type is the spec and the locator. Locator can be multiple things. Has those two important functions, and then that's basically how the interface works. So that's a field. So now what's a message? Can anyone guess what a message is? It's a bunch of fields. Yeah, pretty much that's all it is, and some storage, right? Which might be owning, like an array, or it might be non-owning, like a span. And the message has functions, actually function templates that get or set field values. Then they just delegate to the appropriate field. So given this design, we can ask about or assert certain properties, right? This gives us some compile time safety. We can say, for instance, you said this field was a uint80, but the storage you told me was 16 bits. So it's possible to represent more than is fittable in the type, right? That's a compile time error. We can say things like that. And various other questions. So that's part one. That's just the introduction, as sort of give you the base layer of what we're going to be talking about. Everyone good? All right, now we're going to move on to talk about matching on fields, right? This is the process of a field some data comes in off the wire. You want to overlay a message type on that and test to see if certain fields have values, and based on that, dispatch to whatever callback you have. Okay. So what is a matcher? Well, a matcher is something that you call it with a message. Here, that's what event, but same thing. And it's a predicate, right? It tells you whether that message matches what you wanted from it, right? So it's a predicate. So it's like, does this field equal this value? Or does this field equal that value? And this other field is in between two values, or something like that, right? It's a predicate. And one of the concepts here, I allowed an opt-in. I find that's frequently, when you're trying to express concepts which might be kind of complex to express, often a kind of easy thing to do is allow types to opt in by providing just a type def inside the struct, right? So this is saying, if you have a using is matcher equal void in your struct, that's kind of opting in to being a matcher. All right. More concretely, here's an example of a simple matcher with the run, right? So this is saying, I'm going to run given a field and an expected value for that field, I'm going to return true if that field is indeed that value. That's what a matcher is. It's just a predicate on the message, right? Which in this case looks at that particular field, tests it for that value. Good? Yes. I'm not going too fast. I'm not going too slow. I'm going good speed. All right. Well, a matcher is a predicate. That's a function. Yes.
Just a silly question. So
Yeah.
why did you decide to stick with like a matcher equal void instead of, true type or something like that?
Oh, I see. Yeah. Well, so it can be any type.
Yeah, I understand.
Yeah,
but
yeah,
in that case,
right,
the
right.
implementation of the concept would be much simpler, I guess. Because you can just treat it as the true type and just force everybody just. I
Well,
mean,
the
perhaps the
okay.
interface should not be dictated by the implementation of the concept, but I mean, why not?
I mean, you could. The concept is pretty simple anyway, I think. And I was copying what the standard library does, right? For what they call transparent,
Yes.
right? Transparency, right? So the standard library calls it transparent. Yeah, Michael.
Is there an argument for using true type and false type for cases where someone wants to opt out? If they know they conform to the concept, but they want to be not available to the concept? They can say.
Yeah, the question is there an argument for using true type and false type to represent opting in or opting out? Possibly. Yeah, I mean, if you were making inheritance hierarchies and you wanted to opt out at at a derived class where a base class is opted in? Maybe? I don't know. Possibly. I've done it both ways. This seemed to me to be the simplest way for this thought. Okay. Well, matches are predicates, which means in a certain sense they are Boolean values, right? We can treat a function that returns a bool or something convertible to bool just like a bool, right? They're isomorphic. And what we need to do to compose these things is to provide and or not class templates that will wrap their matcher types and give us a expression template, and they'll implement the operator in terms of the call operator in terms of their underlying matches that they're putting together. Yep. Well, you can guess what's coming, probably. Here's and. It's really simple, right? Given two matches, the call operator is going to, guess what? Run them both and add together the results. I bet you can guess what or looks like. Looks guess what not looks like. Yeah, probably. It's even easier, right? Yeah, so given these three things and then overloading and or not to get the appropriate type, you build this expression template tree, right? And this is composability, right? This is, notice these are still matches, right? These, I left out the is matcher. I left out the is matcher, but these are still matches. In the code they are. That's my mistake for the slide. Not everything in the structure is on the slide, but these are still predicates on messages, right? Okay, so there's a design decision that I made here, and I tried different things. So notice that these ands and ors, these are still binary, right? And takes two matches, or takes two matches. I did experiment with making them variadic at certain points during implementation. I decided to stick with binary because it turned out to be much easier to reason about transforming the expression tree. Okay. Here's the operator overloads that you would expect, given what we've seen. They just return the class template of the appropriate type, right? All good. Okay, that's what matches are. Now what? Okay, so we have an expression template that represents some combination of matches that we can run to be a predicate on the message, right? And it might look something like this. It's an expression tree saying we've got match A and not B or C, right? These are just like Booleans. Well, this is fine. Sometimes, due to another library, we know before evaluation of this predicate that a certain matcher is always going to be true, because in another library we've like indexed on that field or something. We've already done a different strategy right before we come to running the matches. So, and in a given code path, we can know there's a compile time in this library. So we would like to take that knowledge at compile time and use it to simplify this expression tree. If we know that C here is true, then not B or C, that whole thing becomes true, and A and true becomes just A, right? If we know that C is true, we don't even have to evaluate the matcher of B. We only need to evaluate A. Well, who here knows Boolean algebra? Practically everyone. Yes. Yes. Everyone's like, what are you talking about? We don't know. So you're thinking, let's simplify the expression. Yeah, sure. Let's use what we know about Boolean algebra to simplify the expression. Okay, so let's think about that and how we would do that in a generic way. So let's think about simplifying matches. How many guinea pigs are in this picture? I'll tell you, it's two. There are two guinea pigs in this picture. One's easy to spot. The other one's But yeah, let's simplify. So in particular, you know, thinking down the road a bit, we're going to have matches that are things like this, less than 5, you know, a field less than 5, or greater than or equal to 5. How does the library know generically how to simplify expressions like this? You know, as humans, we can look at that first one, less than 5 or greater than or equal to 5. Well, that's always true, right? That expression. As humans, we could say that. How are we going to represent that to the library? This is what the next thing I was thinking about. And with these expression templates and overloading the operators, we made it easy for people to write expressions which might get large, right? And we kind of want to boil them down to do the least work. Well, all right, whenever I come up against a problem like this, I think, well, let's start easy, right? Let's define the atoms. And the atoms here are just true and false, just like in Boolean algebra. Except in matcher land, I call them always and never. And they they do the obvious thing. Always matches, no matter what you pass it, and never does. So seems like a useful place to start, right? So now we know that if we know that C is going to be true from some previous operation, we could replace it with always and then simplify the result, right? And we know how to simplify Boolean expressions that have true and false in them like this. So let's try and write a simplify function. Now at this point, I chose to use tag invoke as a mechanism. There's some noise on this slide. Basically, you can see it says that, so simplify, right at the bottom, simplify, that's a function object, right? And its type is this struct. We happen to be defining the type in line with the declaration here. And it's a function object that has a function call operator that takes any old arguments, right? And then has a no except and a decal type. That's the noise. You can kind of ignore that. But it's going to call tag invoke. And it's going to pass itself as the first argument and then the rest of the arguments. Is anyone familiar with tag invoke technique? Ruslan. Okay. So in a nutshell, why do we do this? Okay. Or how does it work? So we define this function object, a tag, and as we saw, its function call operator will call tag invoke. Now tag invoke is, there's no function called tag invoke just hanging around in the global namespace. Tag invoke is provided often as a hidden friend for the overloads that you want. So inside the and inside the or structs, we're going to give the overloads that take as the first argument the simplify t, right? You can see the tag invoke, this first argument is a simplify t. Now, because it's only defined in those structs, in those same namespaces they're in, it's going to be found only through ADL. This tag invoke actually uses ADL for a good purpose. Spent most of my career cursing ADL, but tag invoke actually works pretty well. So does everyone see how this works? There is more C++ noise that could be added, but this is the basic idea. At this point, is everyone happy with tag invokes? Everyone see the mechanism here? Okay, good. Okay, so I have a couple of slides, like why would we do this, right? So this works, but why would we do it? Why, in particular, why wouldn't we just say, well, you need a member function called simplify? That's going to be the obvious thing to do. Why would we go to the trouble and extra C++ noise of having a hidden friend instead of just a member function? It's a good question, and maybe in C++ 23 and later, we might do that. But until C++ 23, with deducing this, it's much easier to handle, because tag invoke here can be a template with deduced arguments, and we can handle all the value categories in one place, right? So that's one reason. Tag invoke gives us the chance to control exact type matching if we want it. If we put a member function in, that's going to be callable from a derived class. We have that is a relationship, which we don't really want here because we don't. The fact that they're hidden friends and they're found only through ADL means they are a small overload set and easier to disambiguate than free functions. This isn't necessarily a point against member functions. And tag invoke is kind of the one identifier that is now reserved, right? That's a big point. To make different libraries work well together, you don't want them using well-known identifiers and taking over that bit of namespace, right? Simplify T here is the thing that is in the library, and that is namespaced in the library. And that, tag invoke with that will only find things that overload on that type from this library, right? So it doesn't stomp over the namespace that might be used by other libraries or application code. Okay, so that's a bit about tag invoke. It's a good technique. It's probably one of the best techniques we have for this kind of thing that we've discovered yet, before C++23. Okay, so that's tag invoke. So here's simplify. So let's go back to what we were trying to do. We're trying to simplify Boolean expressions. So let's write the default simplification. So the default simplification is nothing, right? Just return the matcher as is. Now this isn't like in the global namespace or anything. This is defined as a friend function inside simplify T itself. Because when it gets passed as the first argument, that's going to find that function. Okay, so if we need default, that's how to do it. Okay, so that was long-winded. Here's actual code that is a first cut at simplifying an AND expression, right? And how would we simplify an AND? Well, simplify both sides recursively. And then kind of the ordinary rules of Boolean algebra come into play. Like we know if either side is false or never, then the whole thing is going to be never, right? This is an AND. If we know that either side is true or always, then we just return the other side. Otherwise, well, we simplify the branches and we just return an AND, right? We can't do any more simplification than that. Good? Questions? Question.
Can you not return always for the last case?
So can you not return always for the last case? No, these matches, the left-hand side and the right-hand side are unrelated. We don't know that the combination of them will always be true. We know that because it's an AND, they both have to be true, which is why we can return never if either of them is never. But we don't know that they'll be true always. In the case of OR, we would. The OR version of this would kind of look like a dual, right? If either side were always, then we'd return always in the OR case.
Nice.
Isn't there really another case though where they both are always that you could return always? Included?
So if they're both always, then the
Oh, really?
second branch here will
Okay.
take care of that, right? Yes.
Yep.
Yeah. John, were you gonna ask something?
I was going to say the same thing.
Well, and you can imagine what this looks like for Ruslan, yes.
So, and actually in this if context where you're checking the type, right?
That's right.
Okay,
Yeah. I'm
because
checking the
otherwise I
type.
cannot see.
Yeah. These if contexts with the checking the types of the matches. Yeah, and perhaps I should have put never T and always T, right?
Yeah.
But yes, you're correct. Okay, so this is and Jason.
Because I saw it used const eval on your UDLs, and I've been wondering this whole time, if this is all compile time templating things, should they all be const eval?
Should they all be const eval? So no, because you can't. You can't call you can't call immediate functions with parameters of context functions, can you? Because
No,
context functions can be at
you
runtime.
can't.
Yeah.
Yeah, you're right.
Okay. Okay. And you can imagine what OR looks like. It looks like the dual of that. And given that, we can code up these sort of normal simplification rules of Boolean algebra that we're familiar with. So like A and true is the same as A or true is the same as true, etc., etc. Well, this is some of them. Yeah, we could do that. It gets kind of wordy. You end up doing a lot because you have to account for left and right on either side. You have to account for commutativity. And we didn't actually solve this problem, right? This is one of the sort of human problems we know how to solve that isn't solved by this. Because these are matches of arbitrary types. How does the library know how to simplify this to always? Okay. Well, the next thing we can do is perhaps customize the not operation in the same way that we customized simplify. If we could customize not, then the library would know that here, not left-hand side is the same thing as right-hand side or vice versa. And if we could know that, then sort of normal rules would allow us to simplify. So let's try customizing negation. So we're going to do that by, instead of not returning a not t, it's going to call negate. Guess what negate is? It's another tag, right? This slide tags always look basically the same. The only difference here is the type name, the variable name at the bottom, and the thing in the no except clause, right? The type is there as well. Other than that, it looks exactly the same. So where we had simplify before, now we have a negate call, right? And we can overload that for various things. And of course, we can write a default. And the default negation is just not around the thing, right? But now there's another obvious sort of thing we can build into negate. Anyone guess what that is? If we're negating a thing that's already a not,
Ungate.
we just return the thing inside the not. So that's what that looks like. Good. Yeah. Okay. So now we have, what were we thinking about? We were thinking about this problem, the less than matcher and the greater than matcher. Well, now we can think about how we overload this negate for a less than t, right? And we tell it, return the opposite relational operator matcher, right? And vice versa. And we could code those all up. But in fact, we can go one step further and we can generalize it a bit. We can say, have a relational matcher, right? And this is going to be customized with the relational operator. Right? So relop here is you stood less or you stood greater. And then all we need to write is that inverse opt to figure out which operations are the inverses of the others. And we've done the whole thing in one function. And then, you know, for ease, we can define less than, greater than as matches in terms of the alias templates that use the relational matcher. Is this good? Bit more code coming on slides, I know, but hopefully everyone's good. Any questions? No, Ruslan, no. Ruslan's happy at the moment. Okay.
Trying to figure out what's going on.
Trying to figure out what's going on. Okay, so we are customizing negate, right? And we are doing that with a tag invoke. And this is one of the overloads. This is the overload for relational operator. This is how we're going to let the library know that less than is actually the opposite of greater than, right? Because that's exactly what we're saying here. When we negate a relational matcher, the negation of it is a relational matcher with the inverse operation, the inverse opt. right? So this is the inverse operation of less than is greater than or equal, and vice versa. John?
Is there any standard mapping of that, or are you just?
I'm not aware of it. No, there isn't a standard. The standard gives us the less, obviously,
Sure.
and all the others, but it doesn't give us the idea of what the inverses are, as far as I'm aware.
That's just a compile time map, essentially.
Yeah, it's like half a dozen lines of code.
Sure.
It's, I think it's actually like, you write a function, I wrote a function, they just have if const extra, you know, return the appropriate thing. And then the types defined in terms of what that function returns. Yeah.
What are the field and expected value templates also?
Sorry, say again?
What are the field and expected value template parameters are used for?
The field and the expected value are saying, so for example, relop here could be stood equal to, right? And the field and the expected value are expressing
Yeah.
the what the field we're going to extract from the message and what we expect it to be equal to, right? Good. Okay. All right. So now we've successfully genericized this idea of negating or complementing. So our library can understand things besides just a not T. So this problem is solved because when the library knows that these things are inverses of each other, left and right hand side, and therefore it will know how to simplify A or not A, right? Because that's a regular sort of Boolean simplification. Okay, next problem. As humans, we look at this and we say, well, we can simplify this to just less than 5, because if something's less than 5, it must be also less than 7, right? So this is my next idea. How does the library simplify this? What was the question?
Other way around.
You have an idea.
If something is less than 7, it must be, or, no, never mind, never mind.
All right, we're good. Yeah, if something is less than 5, it must be less than 7. Okay. And here's where I give you a quiz. Okay, don't worry, the questions are really easy, I hope. No, they really are. And the question I want to ask is like, can I make it, right? If I have an A from somewhere, where, and I have a function from A's to B's, again from somewhere, can I make a B? It's not a trick question.
Yeah.
Yes, of course. I would call F of A. Okay. If I have an A and an F from A to B's, can I make a pair of A's and B's?
Yeah, sure.
Sure, why not? Assuming A is copyable, which is fine. I'll just make the B using F of A. Great. Next question. If I have a variant of A and B and a function from A to B, can I still make a B?
Maybe.
Yeah. Yes.
Yeah.
Yes.
I mean, either it's already in the variant, in which case I'm done, or there's an A in the variant and I can make a B using the function. So what am I talking about?
Oh, no.
You just did Boolean algebra.
The types of.
So here's a question. What does that arrow mean? What does that function arrow mean?
Implies.
It means implication. Maybe you didn't know that, but it's just what exactly what you did.
I just thought you were trying to make function pointer syntax even harder.
What do you mean even harder?
That's because I expect to see trailing return types on function pointers.
Oh, yeah. So this, sorry, this syntax? People aren't used to this syntax.
It's beautiful, Ben. It's beautiful.
I agree.
This is like a decal type. Auto star in parens is a rune that means function pointer. Just learn that. And then you have function arguments, arrow, function return type.
It's gorgeous.
That's it.
Yeah, please, straightforward.
It just took me like a minute to realize what that was.
Yeah, just that's what I think that is. Auto star is a rune. It just means I'm defining a function pointer.
Oh.
Ruslan.
But I
yeah.
guess the syntax doesn't work for pointer to array.
The syntax doesn't work for pointer to array. I'm only interested in functions right now.
Yeah, but I mean, like, you cannot just use it
Array of function
consistently,
points.
consistently in your library if you have both pointer to function and pointer to array, for example. I mean, that's cool, but how to spread it? I'm just thinking.
Okay, well, sure, we can talk about that later.
Yeah.
So function arrow means implication. It's the same thing as implies arrow. Let's look at these questions again so that I can convince you of this, in case you're doubting. When you say in C++, I have an A, the Boolean interpretation of that is A is true, right? A exists. I have a value of A. When I have a function from A's to B's, the Boolean interpretation is A implies B. And the question, can I make a B, is simply saying, is B true? This is left-hand side and right-hand side here are saying the same thing. They're isomorphic, right? And the pair of A's and B's is saying, in the last line, is A and B true, right? There's a pair of it. This is what you've heard of sum types and product types. Pair is a product type, and product types are isomorphic to and terms in Boolean algebra. And the same thing for a variant here is a sum type, and those are isomorphic to all expressions in Boolean algebra. So when you say I have a variant of A's and B's, what you're saying is A or B, that expression is true, right? And then we're saying A implies B, and then is B true? And if you think about this in Boolean algebra, if you say A or B is true, and A implies B, think about whether B is true in Boolean algebra, and you'll come up with the answer, yes, it must be, because either the B is trivially true, in which case the OR is true, or that A is true, making the OR true, and therefore the B is true because A implies B. Cool. All right. Anyone know what's on the next slide? This is what we call this correspondence. This is what it means. This is what type algebra means. It's Boolean algebra, where existence is truth and non-existence is falsehood. And sum and product types are or an and everything you know about programming implicitly, like you answered those questions before I told you about the Boolean algebra correspondence. Everything you know implicitly is Boolean algebra, right? That's it. You already know because you're programmers. Okay, so what is implication? It's another Boolean operator. It's just like and or. It has a truth table, right? It's a function. It's a Boolean function of two Boolean values, and we can write the truth table. So here's the truth tables for and or, and in the last column for implies, right? So it's just a function of two Boolean values, and this is what it is. And if you notice, you'll see it's equivalent in the truth table to not A or B. Everyone happy? Everyone happy, even though they've been duped into doing Boolean algebra. So here is where you have to sort of rewire your brain a little bit, because it's natural to think about implication as an idea in English, if you like. If A, then B. But really thinking about it in terms of an operation, like A implies B is an expression which has a truth value, right? Is the easier or more consistent way to think about it. Now, there are two facts about implication, in particular, that I want to highlight. The fact one is that X, any value, implies true. If we look at the truth table and I grayed out the lines that don't matter, you can see that X implies true is a fact, which is to say the expression anything implies true, that expression is true, right? So 0 implies 1, that's false implies true, that's a true statement. True implies true, that's also a true statement, right? So it's true to say that anything implies true. Yes? Frowns. This is where you have to think a little bit, but hopefully, yes. Yes? The next part is a little bit more strange. False implies anything. Right? And again, we see this from the truth table. False implies anything is a true statement, right? False implies false is a true statement. False implies true is a true statement. This is a non-intuitive thing to grok as a human, because you think false implies anything? Okay, so if I ask you what color is a unicorn, and I tell you all unicorns have pink polka dots, that's a true statement. It's vacuously true because unicorns don't exist. You know, the only ones you've ever seen are in movies and probably white. But all unicorns have pink polka dots. That is a true statement. Okay, that's a bit flippant. Let's look at another way of thinking about it. Let's take the statement, if it's raining, the ground is wet. The question to ask is, what would make this a false statement? Right? This statement would be false if it were raining and the ground was not wet. If it wasn't raining, this statement is not false, right? It not being raining doesn't have any anything to do with this statement, right? If it's not, and if it's not raining, the ground might still be wet for any number of other reasons, right? Here's another explanation yet. So the statement, if it's raining, the ground is wet, is another way to say the set of times when it's raining is a subset of the set of times when the ground is wet. Right? That's kind of easy to take. Okay. Here's what false implies anything looks like kind of in programming. You have some struct and that represents false. You cannot make a value of that type, F, right? And I put in a couple of constructors. In the first case, there's simply no syntax to call this constructor. There is a non-deduced template parameter on the constructor. There is no syntax to call that, right? In the second case, you call it and it just goes into an infinite loop. Either way, you can't create F. So this is kind of false. And the question we ask is like, false implies X means we can write a function from F to X, no matter what X is. And the answer is yes, this type checks, this is a cromulent thing to do. Just from the definition of what we've been saying. Okay. So where am I going with this? Implication is important here. And it's a building block for what we're going to do to genericize our library. So let's look back. Jason,
Did you actually do that thing on that last slide?
did I do that thing?
That thing. I'm trying to make the thing not constructive.
I did, yeah.
Wouldn't it have been more straightforward to just delete the destructor?
Delete the destructor.
I mean, the constructor or the destructor.
Delete the constructor. Maybe? I don't know. These are two ways I know to make it definitely unconstructible. There's tricksy things in C++. I'm not sure a deleted constructor might not be.
If you delete the default constructor, then you.
Does that make it not an aggregate?
Huh?
Does that make it not an aggregate? There's strange rules around
If you have a
aggregate.
constructor at all, it's not an aggregate anymore. So if you delete it, mention it.
Okay. There
Sorry.
could be other ways to make something which is not
I'm
constructible.
tired.
I think deleting the destructor,
Deleting the destructor.
I think deleting the destructor does.
Yeah,
No, you can still.
Still do it and leave it.
Yeah, delete
can,
the default
okay.
constructor is what I meant to say.
Okay, so there might be some tricksy ways to make things unconstructible in C++. These are two examples. These aren't necessarily all the ways. No, it's good.
Sure.
Okay, let's look back at this truth table. So this is the realization I had. If we can say that A implies B is true, so we take out that third line where it's false, and we look at this table, we see that A and B is the same as A, and A or B is the same as B, right? So we're going to use implication as a building block to genericize this library and simplify. Okay, let's see how that works. So we know as humans that there's an implication between these two things. If we can state this in code, then we can simplify the expression because we already know from the previous truth table what that means. So we're going to make an implication customization point. This is what you've already seen. You know, it's another tag. You can see that the only places it differs is the type name, the variable name, and the type name in the middle there. Does exactly the same as before. So the default behavior for this is, well, X implies X if they're the same type. Otherwise, in general, no, right? So this is what this is saying. One matcher implies another by default if they are the same matcher. Only in that case. That's true. We can encode up those very general X implies true is true. That's saying anything, the second argument there of the first tag invoke, implies always, and that's true. And likewise, never, the matcher that is false, implies anything. That's also true. Right? Those are the basic rules of implication. Are we all good? Deane not? Now, if you code this up, you'll notice that it's actually ambiguous if you try and call it with never implies always. So we need an ambiguity breaker, but we're down to concrete types now. This isn't even the template. So that's fine. We can just supply that, and that breaks the previous ambiguity. Because you can see, like, if I tried to say does never imply always, it would match both of these with equal precedence. So we just need to break that ambiguity. And that's what that is. We doing well, Brian?
Sorry, false implies true is always gonna break my head.
Yeah.
That's true. Yeah, it's non-intuitive, but it is a true statement. False implies true. So, okay. So what does it look like for and or? Well, or you know, does X imply or? Well, X implies or if it implies either the left-hand side or the right-hand side of the or. And the other way around for and. Does and imply X? Well, yes, if either the left-hand side of the and or the right-hand side of the and implies X. And this looks easier in code than it looks maybe in Boolean algebra, but if you do the Boolean algebra, you can satisfy yourself with that. This is just what the kind of thing looks like. So we're saying X and Y implies A. That's the same thing as saying not X and Y. Oh, that should be, sorry. Implies, remember A implies B is not A or B. So that's that first step, definition of implication. And then we just push in the knots with De Morgan's laws and we distribute and we come back to two more definitions of implication at the end. So that's the proof, if you like, the Boolean algebra style proof of the and function here. And or is even easier, it's like one line less. I didn't put it on the slide. Now we can write implication also for these relative relational matches, right? So imagine that this is less than 5 and less than 7, right? Less than 5 implies less than 7 because 5 is less than, actually less than or equal to, but 5 is less than 7, right? We can run the relational operator itself on the values inside the two matches to discover the value of the implication proposition. And we've already taken care of the case where they're equal, so we actually don't need to sort of convert the less than to less than or equal to. Okay, so now the library knows that X less than 5 implies X less than 7. And similarly, we can write some implications between matches like less than or equal to and strictly less than. you know, this is very similar to the previous slide. This is saying basically an implication between those two in terms of their expected values. And similarly, we can do that for other relational matches. Okay. So now what does the simplify function look like for and? Well, instead of like hard coding never and always, we can write it in terms of implication, right? So we simplify left and right hand side, as we've seen. If the left hand side implies the right hand side, the and proposition is equal to the left hand side. Similarly, vice versa. If either side implies the negation of the other side, we know the and must be false. Otherwise, we can't simplify. We've got the base case at the end. Everyone cool? Yeah. And it turns out this is all we need, right? We've customized negate, we've customized implies, we've coded up those few simple implication rules and negation rules, and we've got those simplification functions that work in terms of the implies for and or and such. And all of the regular Boolean algebra, you know, falls out of this, like the identities, the annihilators, or the absorptions. All those rules you find when you look up on Wikipedia, they can be expressed like this. Phew. This was a good point to reach. Is everyone happy at this point? Does everyone have questions? Everyone's got stunned silence. John.
So it seems like the compiler should give you some of the earlier layers of this kind of through the optimizer.
It can in some cases.
I'm
Yes.
curious where it falls over. Like obviously
Well-
the implication stuff, I wouldn't expect it to get any of that.
Well, I don't know how the compilers are implemented, but remember that we are building an expression tree, and then we're using a different library, like an indexing on one of the fields, in order to take things out of the expression tree. And at that point, we want to simplify. So, like the point where we're doing the simplification is removed from the point where the compiler is actually, I don't know, considering the tree for the first time. So,
Oh, okay.
you know,
It's not a
I don't know. I wouldn't want to rely on the compiler getting all of this.
No, I certainly don't think it could. I was just more curious than anything where it.
I mean, the compiler can do things like if you write plain old Boolean expressions, like if you write x less than 5 and x less than 7 as a plain Boolean expression, the compiler will only check that it's less than 5. I don't know what the internals of the compiler are doing to make that optimization, but yeah, the compiler can see through things like that at the plain Boolean expression level, not necessarily at the matcher function level. Okay. So we used implication, and you know, there was a paper by Walter Brown suggesting that we add implication to C++. A lot of people saw this paper and said, well, it's just not A or B. Why would we add a new operator? Well, this is why. It is equivalent to not A or B, but how would you have done this by evaluating not A or B? Maybe it's possible, but we were using implication as a building block. It wasn't useful to rewrite implication that way. We were warranting the truth of implication in order to simplify these expressions. Not A or B wasn't really a form we could use. At least I don't see how. Here's another thing I realized about this after the fact. This implication function is a higher order function. We're using it with matches. Matches are functions. But most higher order functions end up calling the functions you give to them. Here we didn't do that because the functions represented in the type. Those functions we use directly as values, and this is sort of a real higher order function that works directly on the functions. Just an interesting sort of thing to note. We don't evaluate them at all. We just warrant the implication between them. Now, I also realized that implication implies an ordering between matches. Okay, so what does it mean for matches to be ordered? We can derive this now. A implies B if we think about what that means that everything A matches, that means everything A matches must also be matched by B. Right? That means that A is less than B. The things A matches are a subset of the things that B matches. And if the implication works both ways, then they're equivalent, right? So this is another way of thinking about that. If A is greater than B, it means that the set of things it matches is greater. So the set of things that B matches is a subset of those matched by A. Not necessarily a strict subset, but that's kind of that in pictorial form. So now we can define a partial order between matches, right? We can given two matches, we can say, well, let's see if left-hand side implies right-hand side or vice versa. And then we have a partial ordering, right? It might be that neither one implies the other, in which case they're unordered. But otherwise, they have a partial ordering, which we can compute with the spaceship operator. Everyone still good? Yeah.
We think about, but yeah,
Yeah. Sorry?
it's weird to think about,
It's
but yeah.
weird to think about, but it holds, right? But now you're like, well, I think I just heard Ben say that A implies B with this glyph, which is how I would normally write it, is the same as A less than or equal to B. And these look the same, and I don't like it. And in fact, these mean the opposite thing if A and B are plain bools somehow. And I would say just think of operators as runes, not glyphs that are composable. Like, I'm sorry, but that's the way mathematics is.
And
Yeah.
May I add a comment?
Go
So
ahead, yes.
actually, yeah, the biggest complaint from C++ standard committee, at least with the people I talked about, is actually the syntax itself.
The syntax,
Yeah,
yeah.
so basically they just come up with some better spelling of it. I don't know, but one of the problems was like you can just misspell it and just put like
Yes.
this angle bracket first and
Right.
equal sign later, and it means completely different thing.
This is because, so arguably, Boolean values should not be ordered,
Yep.
right? They're ordered because of C, because of the history of like meaning 0 and 1, right? But arguably, like less than is meaningless if you're between true and false, right? It's only meaningful because true maps to 1 and false maps to 0. Yeah, there were also people who complained about the syntax here of like the regular implication, like equals greater than, because they're holding out for like shortened lambda syntax or something. And they think it might interfere with the grammar. Does function arrow interfere with operator arrow? No. So why should this interfere? I don't think it should, but there are
Sorry, so complicated.
yeah. Okay. Anyway, implication gives us this ordering, which is what it is. Okay. Now we have a library that can do pretty good simplification. But you know, you're thinking, you know, this is Boolean algebra. We talk about Boolean algebra. There's a couple of things that spring to mind, right? We haven't used these things yet. These are mostly unused for simplification. In particular, De Morgan's laws and distributive law. These come in handy for other transformations. And one of the most useful is the so-called sum of products transformation, right? So this is saying a sum of products is what it sounds like. It's an or of and terms, if you like. It's called disjunctive normal form if you go to Wikipedia. And a Boolean expression is in this form if it's a disjunction, like an oring together of and terms or single terms or not terms, right? So here's some examples, right? At the top level, we have ors. Underneath that, we don't have ors, right? Hence, it's a sum of products. Okay. So to convert an expression into that form, we can recursively apply distributive law and or De Morgan's laws, right? And hopefully you remember what they look like. distribution of and over or just looks like expanding out, right? And De Morgan's law is where you push the not inside the term and you take the dual operation and you knot the terms. Guess how we're going to do this? It's another tag invoker. We know what they look like. Again, the default is no transformation. And so we just need to implement those transformation overloads for the and, or, and the not. So for the not, this is where we apply De Morgan's laws, right? We push the not inside. We negate, we do the appropriate thing. If we're knotting an and, we turn it into an or with the not on the inside. If we're knotting an or, the other way around. Otherwise, no need to do anything. Okay. If we are looking at an and term, well, it might have ors inside it, right? So we're going to convert the left-hand side and right-hand side of the and term into a sum of products respectively. And then if either one of those is an or, we will distribute over it and do the right thing. So this is the overload for not uses De Morgan's laws. The overload for and uses distributive law in the case that you're anding over an or, right? You don't need to look at these too closely, but just sort of hopefully they match up with what I'm saying. And for or, well, it's even easier. It's already in the sum of products form. Like it's an or of something. We don't really care what's inside because it's already an or. So we're just going to recursively apply. And of course, what comes out of the sum of products is itself an or, so we can safely or it together. Okay, so the sum of products form gives us this form where we can then, we've got A or B or C or D. We can effectively, because this is a disjunction, we can separate those and attach, we can evaluate those separately, sort of thing, and split them out. That's why it's useful. Okay, so we're almost at the end of the talk, but I wanted to give you a window into the follow-up talk. So I've talked about like the concept of indexing on a field. We have another library that does this. The details of that are the other talk. But again, what I started with, the upshot of this is that when you've indexed on a field, you know a priori that it's already going to be true. It's one of the terms potentially in this matcher you have that's already true. So you would like to remove it, right? You would like to walk this tree and turn that C matcher into an always matcher and then do your normal simplification. And it all happens at compile time. How are we going to do this? I'll give you one guess. No, somebody said tag invoke. Somebody said it. Another tag invocable for removing the terms, right? Here's just what the default is. It's just like recursion with identity. So we're going to recurse into the left-hand side and right-hand side of each and an or the not. And when we hit one of those, when we hit equal to, right? Is the equal to matcher, which is a relational matcher, but has that alias. We're going to say, well, if we're looking to remove something which is indexed on this field and we're matching that field, turn ourselves into an always, right? Otherwise do nothing. That's how that's working. So now I just want to go back to the previous slide. The library that expresses these fields and messages is an entirely separate library in a different namespace from the one that expresses the matches. All that simplification, the and, or, and not, and all that. Some of the tag invoke objects are in the match library because they're kind of fundamental, like simplification, implication, negation, those things to do with Boolean algebra. But this thing about we've indexed on the fields and we want to remove those terms, that stuff lives in a different library, and the match library needs to know nothing about it, right? it just, that's one of the beauties of using kind of separating this out and using tag invoke. The match library doesn't need to know anything about removing terms. The message library is in charge of that. And then once it's done its job, it can just simplify the result. Okay, that's pretty much the end of this talk. The follow-up talk is all about how indexing works. That's Luke's talk. There's more tag invoke, there's run length encoded bit sets, there's a lot of bad hash functions involved and compile time strategies. But kind of the conclusion I reached here was, so firstly, decoupling types from storage is often, I think, a good idea in this type of library. And I really discovered some interesting things about Boolean algebra. You know, like I go about my day-to-day programming. Most of the time, like any programmer, I'm concerned with like figuring out how to convert a type from this library so I can call a function in this library. But I got a chance to sort of go back to basics and think hard about what Boolean algebra actually means and discover that it could help me out. And I hope it's been enlightening. Thank you very much. Yes.
You know, I was really hoping seeing some examples.
Exactly.
All of this code is open source. It's Intel's compile time initialization of good library. It's one of the subdirectories in there. You can see, you can go to that GitHub repo, and you can see a plethora of tests.
Is it possible to provide a link in the Discord?
Yes.
But actually, you showed a lot of implementation examples. Implementation experience. But when we just see the talk, it would be just great to see the idea how it looks from the user perspective, not from the implementer perspective.
Yeah, absolutely. Well, if you have a minute, maybe I can.
While you look that up,
Developing the library, you know, is the kind of job of like making the implementation nice for developer you work with, but also make the user interface nice so you can easily use it and enjoy it. And we always fail with C++ standard library, by the way. Yeah.
So, you know, what this looks like when you're using it. For example, when we're making a callback,
Can you please enlarge it a bit?
yeah, I will when I get to the code.
No, thank you.
Now it's too big. Can you make it smaller?
Deleting the default constructor is the easiest way to do it. You want it.
I actually was
Is that a good thing?
but it's 25
This is a good size, yeah.
That's a good size.
It's a deleted
there, but we 25 became. Oh,
Yeah. You didn't actually make one.
So here's an example of how we make callbacks.
Not the same as constructing an
Yes.
object.
So this is an example of a callback, has a name, and here's the message definition. This is saying this first argument of the callback is the matcher. So it's saying if the ID is equal to some constant and the field called F1 is equal to another constant, then call the callback, right? And this is the matcher that resulted, and of the two equal twos. If I scroll up slightly more, careful because it scrolls very quickly. Yeah, so this one, you can see I said the ID field greater than hex 80 or the ID field greater than hex 90. I mean, these are tests, so take of that what you will. But you can see that the matcher that came out was just greater than 80. Like it simplified away the greater than 90 part. So this kind of syntax here is a kind of natural syntax for people to express what constraints they have on the fields, and the library simplifies that down to the minimum, right? So that's kind of what the code might look like. Yeah, sorry, Lenny, yeah.
Can you do variable length messages?
Yeah, can we do like flexible arrays and things?
Yeah.
That's not a concern for this library, but effectively you do that by having different message definitions that like you can, because the storage and the message types are decoupled, you can like do the test and then effectively overlay the view of the variable length or the appropriate length.
Oh, okay.
That's the kind of way we use that.
In a real life application, how much does it affect compiling?
How much does it affect compile time? I don't have a good answer for you there. It affects compile time no worse than all of the other compile time things we're doing. I can say. Yeah, it generally, I mean, to be honest, the most. Yeah, you're composing a bunch of matches. Where this shines is not so much this syntax, because you tend to have fairly simple constraints at this level. But the point is that it's in the form that we can remove terms, like I showed at the end, and that's where the real power is, because like I said, there's a separate library that does like indexing on fields for really fast lookup and dispatch. And you can have your callbacks separate and your constraints on the callbacks separate from the indexing on whatever you like, and then they come automatically out of the callbacks. That probably involves like that mechanism is fairly compile time heavy, it has to be said, but like I say, we're doing a bunch of stuff at compile time, and this I don't think is really any different from the other stuff.
I see.
Yeah.
So you said that you're using tag invoke, but in C++23 there is deducing this. So I'm wondering if you would write it in C++23, would you still use tag invoke, or do you use like a member function, or and why?
Yeah. So if I had C++23, would I still use tag invoke, or would I use deducing this because deducing this gives you the easy or the easier value category handling. I would probably still use tag invoke because I don't want to be dealing with class hierarchies, and I don't want that accidental calling of a function in the base where the derived class hasn't overridden it. So I want my types to be nailed down in this case. So I probably still use tag invoke. I guess reducing this would still allow me that by constraining the templates. Nah, I don't know. It's a toss-up. I don't have C++23, so I don't know. And there's frankly, tag invoke is, although a new technique, it's an older technique than deducing this, because we don't yet have deducing this. So it's easier to teach people in some ways. Dave.
So I don't need to filter on incoming messages or search through incoming messages, but I need to filter or search or match on other things. It seems to me that this is well on the way to being something that is really just a generic Boolean algebra expression template compile time thing, right? Or maybe I should ask the question, how close is this to being something that you could put up simply as the Boolean algebra equivalent of eigen, where it figures out all the loops in the right way to rearrange the expression that's written in a natural way, but it figures out at compile time what the most efficient way to do it is.
Could be.
I'd like one of those.
Yeah, maybe. Doing it with yeah, I mean, assuming you mean like this is dealing with predicates, right? Because just doing it with regular Boolean values, the compiler
Yeah,
can do
compiler
that
does that.
compile time, like
But
you
if
can
got a
actually
whole bunch
compute
of,
it.
if we got a whole bunch of
Um,
predicates
But yeah,
that you're putting together, that might be really slick.
maybe.
So you're asking for compile time prologue?
Compile time, was that Ashley?
Yeah.
Yeah, hi Ben.
Hey, how you doing? Yeah, maybe compile time prologue.
Just what everybody.
All right, well, thank you all, and